of Science and Technology and Research, Guntur, from July 2018 to November 2019. And he was a research fellow at MIT campus, Anna University, Chennai, from 2014 to 2018. And he was assistant professor at NIT Puducherry, Karaikal, India, from January 2014 to May 2014. He was a lecturer at St. Joseph University in Tanzania, East Africa, from September 2009 to October 2014. And he received some awards and honors. He received DST Purse 2 Fellow from January 2015 to March 2016 at MIT Anna University, Chennai, and he received of UGC JRF Fellow from April 2016 to June 2018 MIT Anna University, Chennai, and he received a Best Paper Award in National Conference on Innovative and Emerging Trends in Engineering and Technology 2015, and he also received Best Project Award in Cadence Design India Contest 2009, Bangalore, and he also received Best Student Project Award in Intel India Scholarship Program 2008. And he published two textbooks and 24 research papers in different journals, and also completed 20 conferences and symposiums. And he is the editor in IAES International Journal of Artificial Intelligence, a Scopus Index journal, from February 2020. He is a co-convener of conferences National Conference on VLSI Signal Processing and Communication from 2019, and he coordinated around 7 FDPs and workshops. He is a reviewer in different journals. He is a reviewer in International Journal of Electronics from 2011 and International Journal of Computation Mathematics in Electronic and Electrical Engineering from 2017, IETE Technical Review Taylor and Francis from 2018, and Microelectronics Journal Elsevier from 2018, reviewer of Circuit World Emerald Publishing Limited from 2018, IEEE Transaction Computer Aided Design of Integrated and Systems from 2019, and also he is a reviewer of 15 IEEE international conferences. Sir, most encouraging and inspiring profile, sir. And
Thank you, ma'am.
and I welcome, yeah, sir. I invite sir to take over the session, sir.
Thank you, ma'am. Thank you for the introduction.
Thank you, sir.
Yeah. My voice is audible, right?
Yes, sir.
Yeah. I'm here to handle the session, FDP session on ASIC design and testing, which was supposed to be handled by our supervisor, Dr. Joy Vasantha. On behalf of ma'am, I am presenting. I am Dr. Sendil Sivakuma, and basically, like IC design, in which we can say complete design that would be designed for specific application that we can say as ASIC, or maybe as a totally new design without having any customized version. For specific application, we do develop such a design like that. So in that, what are the different types available, what are the features available, and what are the disadvantages available in different types? That's what we are going through, going to see in the first half of this session. And second half of the session will be we will be discussing about how we can go for testing and what are the basic strategies available and different methodologies we are following in testing, and what are the basic tools available that also will be seen for testing. That's what content I have prepared here. So as a first part, we can start with ASIC design itself. ASIC is a application specific integrated circuit. So by the name itself, we can say for a specific application are totally new, which may be not used in any other place. No standard any circuits we use in that design. Only for our specific design, we go for designing from the scratch, we can say. So as a name indicates, ASIC is a non-standard integrated circuit. It is not a standard one or maybe already made. So here completely are going to have as a new design from transistor level. We are going to we supposed to develop. So that is designed for a specific use or a specific applications only. But nowadays we have like many customized versions also for that. So here we can say this is particularly we go for large production. We know IC basic ICs we are using mobile phone, laptops, and all the electronic devices. For specific application, if you start to develop on IC, the total cost that you spend for that will be too large. So ICs also nowadays we are getting with very cheap price through mass production only, and we know that every year like that number of transistors that you are using also getting increased as very large income. So that also we have to consider in this place. So if we go for specific application which may be used for very few places, then the IC price also getting increases. So most of the IC designs we go for like ASIC based designs, we go for large production run only. So that contains like very large part of electronics that we need like on a single integrated circuit. So ASIC basic ICs are small ties that we don't use in all the places. When they go for mass production, small like ties also they go used to manufacture small ICs for control or maybe like basic implementation purpose. And a chip for satellite, which is very sensitive, specific application level we used to develop. And also we used to you need to handle the large interfacing circuits also, memory or microprocessor. These places also we use this kind of ASIC based design because the characteristics between the specific application get different, so we have to customize completely or like we have to design completely. So here a chip may contain microprocessor cell also with other logics there also we use this ASICs. These are the different types that we have. So ASICs, basic way we can define this as full custom, semi-custom, and programmable ASIC design. Full custom, completely as a new design. Each and every block we used to design. Semi-custom, some standard cells we can have. And few connections are maybe like interconnections we used to do completely in custom way, like how we need our application or based on our application. And another one completely programmable that we can do as per our application. We don't have to connect anything newly, just to program the device that will be useful for us. So there's a basic way in full custom. We will be discussing completely what is full custom and how we design, what are the basic things we have to consider in the full custom design. In semi-custom, further we have another two types. One is standard cell based, another one is gate array based. In gate array based, we have another furthermore three subdivisions which are channeled or channelless and structured gate array based semi-custom ASIC based. And programmable, we have two different parts. One is PLDs, another one is FPGA. These parts we will discuss one by one. And what are the complications are available and what are the design procedures available for this. So basic way, we have three different types: full custom, semi-custom, and programmable. So this we can say as full custom ASIC design and semi-custom ASIC design and programmable ASIC design. So full custom ASIC design, logic cells, possibly whatever we use in the IC, we used to customize. All the mask layers also customized because you have to develop a complete IC from the transistor level. You have to customize only for the specific applications. So one of the major advantage that we get is we won't be having any unwanted blocks inside your IC. You are going to develop this IC only for the specific function. So what are really important are required for the specific application that only we used to have. But another major issue is that you have to design from the scratch. So each and every circuit, even small cells that you have in the full custom ASIC to be designed. We know even small transistor, if you want to develop, we will be using like 5 to close to 10 mask layers. All the mask layers to be customized in the manufacturing process. And we don't have to actually confuse also. Design also takes some set of time. After that, you have to go for fabrication. Both the time duration we together say yes, total time to get the full custom ASIC. So here designers also, they have to characterize all the functions, because we may have some requirement with a specific speed, or maybe like basic idea of like this maximum speed we supposed to have. This must be a area. Some idea we can have that. Within that, you have to design and you have to recharacterize also. So for that, you may have to spend more time in the designing part itself. Even for a small block that you have to design, for that also it takes more time. And customizing all the ICs, like including analog circuits we may have, and digital circuits we have, large memory cells also we do have, mechanical structures also we do have with IC, all should be customized. So full custom ICs normally most expensive if you don't go for mass production. And during manufacturing also, manufacturing and designing, all the complications are all the cells that will be designed from the scratch. These are like basic things we have to remember for the full custom IC design. And the total time, normally with the basic IC, this is a basic information only, not with the advanced ICs. Manufacturing time, that is not at all considering with time required just to make the IC, not including the design time. So make the IC itself, because you are going to have multiple mask layers. So that alone considers almost typically like 8 weeks for getting a full custom IC. And design time also more. It used to be like very large in time. So here specialized full custom ICs are often we go for specific application only, which either we go for like a defense purpose, or particularly like so much important functions, or we must go for a mass protection. These two are the places where we use a full custom ASIC designs. So full custom ASIC designs, all of the logic cells and even circuits in the, from the transistor level, and for layout specifically for only one ASIC, which is our application. Here. Also, designers avoid using the pre-tested or pre-characterized cells. We may have a standard cells, which may be in any form, either soft core or maybe hard core, or like fine core model we can have. And most of the ICs nowadays, you can see even manufacturing of some mobile models, you can understand nowadays in the market strategies. When they start the product itself, they announce the release date. So they have some pre-calculation. They cannot design complete your mobile phone or whatever the ICs we are using inside from the scratch. So they collect the standard cells. With that, they just connect together and then they bring into the product. But here in the full custom ICs, we don't do like that. We never use any pre-tested or maybe pre-characterized cells, or as a part of our design also. We have to design each and every cells from new. And in the next also, you can see existing cell libraries are not fast enough. Cell libraries, many standard libraries are available. So day by day, we will be having like different characteristics and different technology we are going to use, and accordingly the speed also get differs. So existing one, if you use that, also may degrade the speed of your design. When the precision is mandatory, with the high speed, we must go for a full custom ASIC design. And the logic cells also. If we use pre-designed the cells, we cannot say that whatever the cells used in the pre-tested or pre-characterized cells will be useful in your design. So here that we can avoid. So logic cells are not small enough previous cells that we may have, that we don't have to consider anyhow we are going to have completely as a new design. Also, it consumes more power when you use like previous technology that must be adapted with your new technology. That also basic disadvantage we can say if we are not going for full custom. So full custom, if the technology is new or so specialized, there are no existing cell libraries we'll be using, and here the ASIC is so specialized function, and we customize and we design each and every cell which is available itself. So here, not all the ICs are going with the full custom design. Very few full custom ICs are being designed because of the problem with the special parts of ASICs that we have. And in ASIC design nowadays, we are getting as a complete system on chip, which will be having both mixed signal circuits, analog circuit and digital circuit, all the interfacing circuits, right? All are available in the single like IC itself. And the next part we have as a semi-custom ICs. So full custom, as we discussed, we don't use any like pre-designed cells. In semi-custom, we use almost all the logic cells are like pre-designed only. Only few cells which may be required for customizing or interconnection or interfacing phasing will be using a customized block. So that is the reason we call this as a semi-custom ASIC design. So pre-designed cells mostly as a tested only. The cell library makes a design and much easier also. And nowadays many like vendors are available who are designing the standard cells. The standard cells also maybe like the semi-custom design purpose will be having two different forms. One is standard cell based, another one is gate array based. One is standard cell based ASIC design, another one is gate array based ASIC design. First one we'll check with the standard cell based ASIC design. As I told, like different cores we say these cells as a core. Those cores we can connect together. In the basic way, if we see like cell based ASICs, or we can say CB's IC also in the simple form. These are all using pre-designed logic cells, either maybe AND gate, OR gate, and multiplexers or flip-flops. These are a few examples only. Nowadays, we have even large blocks as a standard cell function that we use directly to design and get a complete application, complete our application. So here one can apply CBIC to the IC and uses as a cells, but it generally accepted with the cell-based ASICs or standard cell-based ASICs we can say here. These cells are available in different forms. Maybe as a basic form like soft cores we can say. Yeah, I told already about cores. The soft cores are customized. You can even when you are using, if you need any modification that you can get, you can do. When you get a standard cell from some vendor or some specific like manufacturer, that cells you can get and you can modify accordingly. The soft core have a facility for that allows you. They will be producing the complete documentation. That means your data sheet also for the specific code that you can use. So here the standard cell areas in a CBIC are built of rows of standard cells. It will be arranged as like constructing a house. And then we will be having interconnections also in between that we can use for interfacing one to other. So standard cells, cell areas will be used in combination with microcontroller or even microprocessors as a very large blocks that we can call as mega cells. And these mega cells always produce a mega function. And full custom blocks also you can have to build the different application easily. And the cores, what I'm saying, like soft core or fine core or hard core, this is also for specific application they develop. That may be a full custom or maybe semi-custom model also. And system level macros also we can get, and fixed blocks as cores and functional standard blocks we can get for the specific function. Many mathematical applications are DSP based applications are fixed like number system and memory. Basically this we can get as a standard cells or cores that we can use directly in manufacturing ICs. These are the simple structure that is available. You can see like the different blocks which are like a standard cells that we are having. Standard cell area 1, 2, 3, 4. These are the fixed blocks that may be from different vendor or maybe the same people. Standardized cells that we use to get to a complete version of our application. So based on this requirement, we will be selecting the cores. And we must ensure that when you are selecting these standard cells, this must be supportive or maybe like you can be able to interface with other blocks in terms of frequency or maybe the speed, that you must ensure before you select these standard cells or fixed blocks. So after that only we will be collecting all the blocks, and then by interconnecting this, you can get your application. So ASIC designers defines only the placement of standard cells. We can place anywhere. This is based on selections only. Like 1, 2, 3, 4 numbers represented. Some may be a memory cells. Few may be like power blocks. Few may be like we can say like analog circuit or digital circuit or some mixed signal ADC and DACs that we can have. We can choose where we have to place. The main aim we know normally in the development of ICs, low area we supposed to have, low power, and much like high speed we supposed to have. So according to that, we can arrange. Maybe we can consider like the cell 1 and 4 are connected or maybe closely connected each other. Too many number of interconnections are available. Then we have to place these to each other, like close to each other, so that we can reduce the interconnection. So like that, as per the interconnections, we can select and we can place the cells also. It is not like a fixed one that we can design. So placement of the standard cells and we can interconnect as a cell-based IC here. Standard cells can be placed anywhere in the silicon. Also, all the mask layers for CBIC is customized are unique to the particular custom or the specific applications that we have. And here the advantages are designers save a time and money we can buy directly, and we can reduce the risk also because they are all pre-designed and tested and characterized for the specific application. So these are the major advantages we can have with a standard cell-based design. In addition, they can be optimized individually. These are the advantages we have. And during the design of cell library, each and every transistor in every standard cell can be chosen to maximize the speed and minimize the area. As I told, like when you get the data sheet, which gives a complete information because you are going to buy from someone else. So these standard cells, all the information be available in the data sheet. By referring that, you can choose the cell. Maybe you have some application or have a planning some application with a specific speed, or the cell which you are selecting is with very low speed. It won't support it won't help you to reach your design plan. So according to that, we have to select collectively, and we should not leave any like unwanted blocks also. That will be like unwantedly increasing the total area also in the semi-custom design. So disadvantages here: time or expense of designing and buying the standard cell library. You have to identify the standard cell first, and time need to fabricate all the layers. You have to interconnect where you have to place placement and fabrication will take little more time. Because semi-custom cells, you have to learn about the cell which is not designed by you. ASIC design, full custom design, each and every cell that you design. So you know like how they can be interconnected. Here you have to learn the standard cell library first. And then we have to go for fabrication or interconnection with other blocks to have a complete custom design. And the next method is gate array based ASIC. So gate array, sometimes we call as like a GA also. Maybe when you are using Xilinx, you can see the structure also. They directly mention as GA here as number of GAs, gate arrays that are used for implementation. And here, gate array based ASIC, the transistors are predefined on the silicon wafer. So specific structure only will be using predefined pattern of transistor, and the gate array is a base array actually. So smallest element that is replicated to make a base array. Sometimes we call them as a primitive cells also. Primitive cells here. So only top few layers of metal which define particularly interconnection between transistors are defined by the designer in the gate array model. So mostly like we'll be using very large size of gate array. So often we call this as like masked connection we used to have. So masked gate array, LGA we can call. So normally designers chooses from gate array library pre-designed and pre-characterized logic cells based on the application that we are going to develop. So logic cell and the gate array library are often we call as macros only. Sorry, macros only. Here base cell of a layout with the same logic cell type only will be having only the interconnect are customized here, which is similar to software macro. Software macro will be having complete as a block. It can be modified when you go for integrating with the other cells. And hardcore, we cannot do that. So these are the different types of MGA or gate array based ASICs available. One is channeled gate array, another one is channelless gate array, and the third one is structured gate array. Yeah, channeled gate array as a first type. So channeled gate array was the first that to be developed. So channeled gate array, it will be arranged like specific rows, and between will be having a space for interconnections. So that we can call as array space is left between rows of transistors for wiring purpose. That we call as channeled gate array. And channeled gate array is like a cell-based IC only. You can see this channel like base cell are available. Between that, you can have a channel also. So this channel only we will be using for interconnection. So both use the row of the cell separated by the channels used for interconnection purpose, because interconnection we have to do with the like all the cells to get the complete like IC. So one difference is that space for interconnect between row cells are fixed in height. These are all like pre-designed only. And in the channel, this is in the channel gate array. So the space of between the rows of the cell may be adjusted in the CBIC cell, that is CBIC model, cell-based ICs. Here channel gate array, that is fixed height. This is a basic difference that we have. This is the structure. So we'll be having different rows which defines the logic circuit or small blocks that we'll be having. And between we are going to have a channel also. In this channel, we can have an interconnection. So these are the features. Only interconnect is customized, the remaining are predefined. The interconnect uses predefined spaces between row-based cells. So manufacturing time between like 2 days to maximum 2 days to 2 weeks, like that only will be having. That is based on how large the application is available. And the next one is channel-less gate array. Here we won't be having any channels like your the previous channel gate array model. You can see like continuously the blocks are available. These are all the base cell or standard cells that we are having. We are not having any channel between that for interconnection. Then we can have one question: how we interconnect one to other? That is one of the major challenge that we have to consider here. So interconnect uses predefined spaces normally in the standard cell, but here in this one channel-less model, we are not going to have any predefined like space here. So routing on the channel-less gate array model uses only unused transistors in the row. So each row in the complete design, custom design, you are not going to use all the transistors which are available in your design. So which are not used, that we can use for interconnection. That is the only way that we have. So interconnections normally we must have very minimum compared to board-based design. That is normally in the IC we have to consider. So the key difference between channel-less gate array and channeled gate array is that there are no predefined areas to set or for routing between the cells on a channel-less gate array. So we have to route over the top of our gate array devices when we have more interconnections. Otherwise, we can use the unused transistor directly to have an interconnection. We have to customize. So we customize the contact layer that defines the connection between metal 1 and first layer of metal and the transistors. These are the basic ways that we have for channel-less gate array connection. So features of channel-less gate arrays are interconnect is customized, remaining cells are predefined. Interconnect uses predefined space between in the normal channeled method, but here we don't use such a model. Transistors we can use or on the top over we can connect. So here also we'll be having 2 days to 2 weeks based on the application size. So when we use an area of transistor of routing the channel is less array, we do not make any contact to the devices lying underneath are simple like transistors as unleaved, leave us unused only when we don't need any specific interconnection through the transistor. So this is the structure. Channel-less gate array, or we can say a sea of gates array in type. The next one, another type is structured gate array. Here there's a structured gate array, or we can say as the embedded gate array, die showing the embedded block. and upper left corner. This block usually be very large only when we consider like place the cells. So this embedded block we used to fix in any one corner only. This is array of base cells we have that we can go for interconnecting with the embedded gate array. So the major features are only interconnect is customized and custom blocks are considered in each design and they are embedded with a circuit. And manufacturing lead time also is between 2 days to 2 weeks only. These are also using predefined blocks. Embedded gate array gives the improved area efficiency and increase the performance also of CBS cell-based ICs, but lower cost, with a lower cost and faster to turn around with mega gate array also. The main disadvantage is that embedded function is fixed only. We cannot change anything further or maybe modify anything. So these are the different types are available in the semi-custom. And the third one is programmable logic devices. PLDs. We will be having many basic memory devices also. That's what we are going to check here. Programmable logic devices are like a standard ICs only. They are available in standard configuration or standard models, we can say. So PLDs may be configured, or we can say simply as programmed to develop our customized or a specific application. By programming the device, we have to develop. We have to we are going to get a customized design for a specific application. So this is also a family of ASIC design only. PLDs use different technologies that allow programming of the devices. This general structure, macro cells, and programmable interconnects also. Initially, we will see all are interconnected only. As a standard structure, we will be having. So based on above application, we can select number of arrays required under PLD type, we can say. Number of cells required to have a complete design that we can have. These are the programmable interconnect. By removing this one, we can disconnect them or we can keep for having a connection. So features of PLDs are no customized mask layers we do need. The only thing is we have to program, that means interconnections we have to program. Also uses a single large block of programmable interconnect. But for the specific application, we have to select the appropriate size only. Otherwise, unwantedly, this will increase the total area. So single large programmable block you can have with the interconnects that can be programmed that is through either specialized function or maybe with a custom way we can do. So matrix of logic macro cells that usually consist of programmable logic array logic followed by a flip-flop or latches to access the data. So basic types you can see programmable ICs, programmable read-only memories we are having. So PROM we can say, or electrically programmable read-only memory, or EPROM we can say that. So many different types of EEPROMs are available, electrically erasable model, which uses UV rays for specialized function. So these logics we can check here. So the first one is ROM, read-only memory, the simplest type. Simplest type, you might be seeing the structure. The basic structure is accessing the specific address type. I'll show you here. Specific type of specific cells only will be having. We can access the specific array also. We will be having some decoder maybe to define the memory address locations. So this will be having a different length of lines which are having number of cells or memory cells, we can say that. So through which we can program. We can access this. These are all giving the row and column address lines. So through which we can access them. So specific cell, if you are selecting R, this is the cell location that you are selecting through the row and column decoder, you have to select it. And on the specific location, you can program this for having either logic 0 or logic 1. That is implementing some specific function. That is programming a specific function. And many ICs, they need like specialized laboratories to develop, and many functions are like user-defined structures also available that we can like fuse connections only. Fuse connections are maybe like the transistor level interconnections that we can have, that we can program through either numbers or maybe removing the fuses, metal fuses be attached between the memory cell and in the read-only memory, that we can fuse by blowing permanently, and the program will be like permanently fixed. Once you fix it, we cannot modify anything. That is a basic model of programmable IC, which is programmable read-only memory, or PROM we can say. Another one is the electrically programmable one, or EEPROM we can say. This is uses like programmable mass transistors. As I told, like mass transistor as a switches they use between that, which characteristics can be applied like altered by applying high voltages or maybe some input to the specific transistor. We can alter and we can select a specific location for storing the data, or maybe like reading the data, read and write function. Both we can do. And then next one is like one can erase the EEPROM either using another high voltage, that is electrically erasable PROM or EEPROM we can say, or by exposing under UV rays, ultraviolet light, we can show that erase the completely or a specific location that we expose. That we can say UV PROM. There is another type of ROM also that we can say as ASIC, mask programmable ROM. This is mask programmable ROM that we have. This is a regular array transistor permanently programmed through the custom mask patterns. So for that, specialized engineers or designers required to program this, are specialized lab also they will use to program it permanently. So you can have a design, you can give your design or maybe the required function as a text pattern to them. Then they will manufacture or they program on the IC, and then they will issue. So embedded mask probe, which is a large and specialized logic cell that also we can use for this programmable structure. And another one important structure in this programmable logic is field programmable gate array, which we use nowadays as FPGAs. This is the newest member in the ASIC family and are rapidly growing, replacing TTL in microelectronic system, basic transistor level models. Even though like FPGAs is a type of gate array, we do not like consider in terms of gate array based ASIC design, include ASICs. We can program with a specific function and directly we can implement on this. So there's a very little difference, like there are like very small difference only we having FPGAs and VLDs. FPGA is usually just a larger or more complex than VLDs, that we can design a specific function or application and directly we can implement on this FPGA. And some vendors are available for programmable ASIC cells, and their products as FPGA are and some call as complex PLDs also. The basic characteristics of this FPGA are like no mask layers are customized, and there is a method which we have programming basic logic cells and interconnections also. So we define everything in programming, and that will be programmed through the basic block or maybe logic cells which are available in the FPGA. So based on your application, you have to select the FPGA also, and nowadays many different versions are available for different applications, also signal processing and low power functions, and many nowadays are supporting for automation functions also. So the core is regular array of programmable basic logic cells that can be implemented as a combination as well as sequential logic cells, which are available in the FPGA. The matrix of programmable interconnects are to the basic cells. Nowadays, like reprogrammable structures also available in the FPGA that also we can use for implementing our function. Programmable IO cells surrounded on the core that helps to interconnect one to other, and design turnaround is like very few hours, even few minutes for small applications. This is structure. Programmable logic cells are available and programmable interconnects are available. So in the programming, you have to define how your application is supposed to look like. When you are programming or maybe dump on the board, it will be configuring into the specific structure, and it allows to perform our function. So these are the like different types of ASICs that we have, ASIC structures that we have. Now, how we design this structure, that is another one major constraint. That's what we are going to see here as a design flow. So sequence of step design that we have to use for ASIC, that we call as a design flow here. So various steps involved. First one is the design entry, how we have to design, and logic synthesis and system partitioning. We have to go and pre-layout simulation, and then we have to plan your flow like for interconnection and placing the cells, and the interconnect between the large cells through routing, and extract the function for resistance and capacitance and the interconnects, and post layout simulation to ensure accuracy in the design part we can have, and then directly you can go for fabrication process. So this is a complete design flow that we have in the ASIC. So as a first one, design entry is a stage or where the microarchitecture is implemented using hardware description language. Popularly, we use Verilog and VHDL and system Verilog nowadays for implementing these functions. Even many functions like nowadays, we have a tool which supports with C, C++ programming also. And many like interfacing functions also supports with Python programming for different automation functions that we have. But popularly with the basic design entry, initially like here design entry starts with the stage of programming or implementing the structure. And before that, we must have a complete specification for our application. So for what the specification you are going to develop the hardware language or maybe hardware description language, and through which you are going to implement the circuit. So in the early days, schematic editors were used for design entry, where designers instantiated the gates, and from that they have to design and increase the complexity of current designs also. So now the use of HTLs to gain the productivity. Like we can program ECE for a specific structure. We have many primitive and standard libraries also, so standard cell libraries also inside tools that we have. That also we can directly use for design and developing the application or the architecture here. So another advantage, HTLs are independent. So directly for the specific application, you can program, and you can interconnect with the blocks and sub blocks level also. Each one you can have. See like many sub blocks you can have. Each block you can define separately, and you can interconnect together to have a complete application. It's not like a large application how we characterize and how we implement in a single shot, which is not required. Here, HTL supports to develop these small blocks also, and that can be interconnected. Standard cells are available that as a subcodes that also you can interconnect in the like when you are developing your design in this. And after developing a complete application in the design level, we go for logic synthesis. So we use a HTL or VHDL Verilog logic synthesis tool that we use to produce the complete netlist for describing the logic cell that we programmed already and their interconnections also. So through logic synthesis, you can verify how the blocks are interconnected, if anything is missing or any interconnections are missing or anything that you defined in your application are missing that you can identify. And system also, before like normally in the programming, we divide our partition the large blocks as a sub blocks we can define and we can integrate together. That's what we call as system partitioning. A large system we don't have to design in a single shot. Each block can be designed and can be interconnected in the ASIC design also as a sized pieces. And pre-layout simulation. Normally this is for basic verification. Next testing we are going to check. In that this we can say as a very basic model or a very starting level of testing that we can say. So we have to check the function, what we intended for and what we are getting, that we have to check. So that is like a functional testing or functional correctness we have to check, maybe function comparison or maybe with the basic model or laboratory structures. If you say like with the truth table, you can check this. This is what pre-layout simulation checking or functional correctness we have to identify. And then we go for floor planning, arrange the blocks of netlist on a chip, to have a complete like a place on the specific area. And then with the placement, we decide the exact location we can replace according to the connections that are available between two different blocks. As like already told, the blocks which are having too many number of interconnections must be placed very close to each other or adjacent to each other, so that we can reduce the interconnections. We should not use large space only for interconnection. So according to that, we have to place the blocks that under the placement procedure, and then make the interconnection between the cells and large blocks through the like a specific area allotted for them. So that's what routing we say. So initial level, if you see like a design entry, we have to go, and then logic synthesis we have to perform to check the structure what you design, and then system partitioning that we use in the initial level itself for developing a design entry, and a pre-layout simulation to check the functional correctness, and then floor planning, placement, and routing for reduce the interconnection parts. We have to perform these functions and place on the specific area. This is what decides the real area that occupied on the IC, or we can say as die in the chip. And extraction, after getting this, we have to extract to determine the resistance and capacitance of the interconnects. That actually changes our function. If we have those resistance and capacitance as RC components, we used to call as very large, means that changes our function. What we are designing, we are not going to have a same ideal performance. So there's variation also, you have to check through this extraction procedure. And then post layout simulation we go for. It is used to check to see whether the design is still work with added loads of interconnect or not. That we used to check here. So this is a post layout simulation. The simulation part, we get this post layout simulation that has a like final version for correctness purpose, and then we develop and we produce the layout functions completely for manufacturing process, and manufacturer will be having different layers for manufacturing of the function. This is what a design flow. Start with a like a record specification, you have to calculate and you have to get all the details, and then you can start designing. So this is the design entry part. Design entry part, you start design that and you perform the logic synthesis. This is design entry Verilog or VHDL system Verilog we will be having. This is like a programming part through logic synthesis, how they are connected. What are the cells or logic cells you are using, or gates or arrays or multiplexer or filters or memory blocks that you are using, all how they are connected to each other as an at least will be having. And system partitioning, you can go for verifying the function, or maybe as per the data sheet that you are having for verification purpose. So here with that, if you have the system partitioning, if you have any issues, you can go again with the logic synthesis and you can perform the system partitioning. And here you have to perform the pre-layout simulation to identify the correctness of your function in the form of layouts. As logic 0 and logic 1, you will be having that we have to verify. If we have any issues, you have to go and correct again. This place you can modify your program to get the correct function, or where you have an error that to be identified. I'll tell you in detail how we go for testing procedure in the next part of this section. So after this, we go for floor planning. So here these are the different blocks that we'll be having in the chip. We have to plan to occupy within this area, and then we have to place in this place. We can adjust based on the interconnection requirements, and then we connect the each blocks together to get a complete or final version of your IC here or die we can say here. And then you extract it for a resistance and capacitance model or RC components that should not affect your function. Then we can go for forced layout simulation. There also you have to check the correctness that should be as per your initial design that you have. If you have any issue, again you have to go for floor planning. It's a cyclic way you have to do until you get a perfect design. So first part is a logic design part. Here second part with a floor planning and placement and routing, we can say as a physical design. This is a complete design flow that we have for ASIC design. So here, like you can see, like first four are logic design steps, and 5 to 9 are physical design steps. And we used to perform both whether to get a complete version of your IC. Okay. So this is a way, like different types of ICs available, and how we can design those ICs to get a complete version of your specific application. And how we test one, what are the testing procedures available? Here we said this is our design, what you are designing, that we can say as is so perfect. What are the basic testing we do, like pre-layout simulation and post-layout simulation we do. If we have any small variation with a circuit, maybe resistance and RC components level, or maybe any parasitic components develop, that we have to identify. Because small variation in each and every block, or even the cell sizes, micro and nano level is increased or decreased, that changes the characteristic of your application. Until it get affect your, like it affects your function, we can say that your output function is so perfect. If this becomes large, that changes the output response, that directly collapse or maybe gives a error in the output. So for that purpose, we must go for testing. Testing also we have different level. How we can test? You can see like this is a complete design. You are going to have this design basic transistor level we have, gate level we have, and blocks level also we have. Each block how we can test, and analog blocks we may have, digital block we have, or mixed signal blocks are available. How we can test those blocks, and testing how we can perform. The basic idea I can select with a simple maybe flip-flop, D flip-flop you can have. As per D flip-flop, you will be having a basic requirement as one clock signal and the input and output. So according to the clock signal, the output will be updated with respect to the input changes. But here as IC, if you select, in addition to that, you will be having an enable signal, reset signal, and other more control signals also we do have. What is the use of that? Basic ASIC design, these are all not required. So if you are adding such additional pins, that we use for testing. That we use for testing purpose. In the same way, not only in the sequential circuit, combinational circuits also, or in the functional blocks also, we do have an additional block or additional circuit to test your actual design. That's what we will be discussing under testing part of this section. So this is the first part that we are going to complete like with this design flow here, which is like very large versions only. These are the sequence of procedures that we have to follow. And the second part starts with the testing. So here testing topics, we go with introduction and testing during the VLSI life cycle, that we can define whether is required only during the manufacturing or after getting as a device also the customer able to test. That is what as I give an example as flip-flops. And VLSI development process basic level for testing, and testing from designer point of view, what they are saying, and how we can model the testing and what are the testing models available. ATG, automatic test generation, test vectors we have to generate. The first level, maybe you may have like experience the pre-layout function. We used to develop a test bench instead of applying each input. How do you test the pre-layout simulation? We are saying you have developed some Varila VHDL function. You are going for simulation. You have to apply some set of input and you have to observe some. You will observe the output values. How do you say this is the correct version, or maybe the pre-layout simulation is giving a correct function? You have to compare the input and output combination. For the specific input combination, you have to get a specific output. If you have any variation, that we say as error. So that is what we are going to do here with like first part, test generation. For small blocks, maybe with the 2 input or 3 input or 4 input even maximum, we can apply one after one. But when you have a very large circuit with maybe some 10 input or like 16 input, 32 input or 64 input functions, that is practically not possible to generate and apply manually one by one to test. So for that, we must have one test generator, that is automatic test generation, ATG, and then design for test, we call this as Dept. We used to represent with a D small f and T to differentiate from display Fourier transform in digital signal processing. So here, this is a one basic model, and that includes the structure for testing the specific application. And then another model, we have built-in self-test, which are integrated with the logic block itself. There's an additional block inside the IC itself. So that helps for self-testing, automatically test and produce the response in the output side. And then synthesis for testability and what other different tools are available for testing that we will see in this part. So here, as per Moore's law, there is a basic function only. Number of transistor microchip doubles in every 2 years as a basic level, and decreasing dimensions also, and micron and nanometer technology that will be using, increasing operating frequency and clock speeds. These are all the basic things that we have with IC. So in this situation, we have to work on testing procedure. So when you are performing testing with the same speed, you have to do the testing also, and increases the probability of manufacturing defect when we have this high frequency. If one clock is missing, or in between some function or some, we are saying like standard cells, additional cells you are going to get from different vendors. So if that is one block is not matching the actual speed of application, that definitely affects liver function. You will be having a different delay, and your output also with a different combination. You won't be having exact output what you are expecting. So increase the probability of like during manufacturing. This is another one big thing that we have to consider. And testing this one also as very like a hard thing. We have to exactly manufacture with the same size, but practically if you add additional dopants, the size of each like layers also get increases. That gives a different characteristics that directly affect your function, and small defect that easily result in faulty transistor or interconnecting wires, that also we have to like consider with the actual like current situation. When you have like million number of transistors, we have to test the block. So just imagine how complex this is. So for that, what are the different steps available? That's what we are going to check here. So faulty transistor or wire to make an entire chip to fail if we have like faulty interconnection. And checking the complete circuit one by one or stage by stage is not practically possible in the large application. So to function properly at required operating frequency we supposed to have. So there is also we have to check, and defect, we can say faulty transistor wire or defect, a flaw or a physical imperfection that may lead for fault, we say as defect here. This may be manufacturing defect. Normally in the IC that results a faulty chip. So normally in the function, it is practically impossible to get 100% of particular kind of IC to be defect free. Few defects be available, we may bypass, or maybe that won't affect your actual function. In that form only we have to perform here. But nowadays many different techniques and advanced models are available that we can use for testing purposes. So testing during the VLSI life cycle, where we do testing typically consists of applying set of test stimuli, that is input, we can say simple in the programming level we can say as testing to the input of circuit under test, any specific application that we have developed for our specific function, or through the hardware description that we are going to test, which we say as circuit under test, while analyzing the output responses. This is a basic idea. This is a circuit we are going to test. In the tool also normally we simulate, and we have to apply some set of inputs, and we will get some response from the circuit.
Sir, sir, I have one doubt, sir.
Yeah,
Sir. Yes, sir. Circuit under test means that during our before simulation process, we have to test the circuit, sir. If you have, yes, sir.
Yeah, after developing the basic functional simulation that we are doing, that also we can say is testing. Testing we do in different level.
Yes, sir.
Each level we have to test to ensure the final accuracy. Main thing is final version should be defect free or high precision we supposed to have.
Yes, sir. If he fails, result means what will be the next step we have to do, sir?
If it fails or affecting our function, we have different technique, something like directly affect or with very small fault may be available that we can bypass. I'll tell you in the upcoming like subdivisions or the slides we can say.
Yes, sir.
And those explanations. If we have some circuit does or maybe some testing or some defect that affect the complete IC, which cannot be identified or maybe taking more time or uses more cost also. In that case, we have to replace it. There is no other option. We have to throw off and we have to
Yes,
get
sir.
a new defect.
Yes, sir.
We'll check the complete structure.
Okay,
Then
sir.
get in some. So this is the basic
Yes, sir.
structure. So first one, input test stimuli. As I told, like when we have large number of input pins, practically applying or maybe generating some section is too hard. So we can have a separate block that can develop the input test vectors. And that also not
Yes,
for
sir.
all the pins. I will tell you with the different sections. If you have large number generating the complete set of input, maybe some 10, if you consider 2 power 10 different combinations you will be having. All the combinations, if you are generating, each input will be taking different time. And each
Yes,
one you
sir.
have to test the complete number of cycles also get increases into 2 power n. So for that also different test generation modes are available. That also I will explain in the upcoming slides. So basic idea, you are having one circuit which you are going to consider under test. We say circuit under test or device under test or board under testing. According to that, we change this expression also. So all this, the basic requirement is some input that we have to apply. For that, we are going to generate, which we call as input test stimuli. That we apply to this circuit, and then we get the output from your circuit that you are considering or maybe under test purpose. And that output also you can test. One is manually by comparing simple comparator you can use. For that, you may have to use a large memory storage that have a predefined or maybe accurate test results or maybe output responses. Through that you can compare, or some characteristic based analysis model you can develop, for that the output will be applied. And after testing this output response analyzer, we used to say ORA, that gives the responses pass or fail whether your circuit is having a defect or there is no defect present in your circuit. So here different stages are available, that is in VLSI development process and manufacturing process and system level operation. But all the structure, these three are the basic structure, where we are going to keep this input stimuli or test generator, and where we are going to keep this output response analyzer, and how we are going to get this output response as pass or fail. So here there is a development process. Just now we saw design specifications we must have and design entry, and then we go for fabrication and packaging, and then the quality assurance finally you'll be having. Each stage we have testing. Design side we have design verification model, and fabrication side wafer test we used to have, and after fabrication also the die used to be tested, and in packaging package test model we have. In each stage, every stage, maybe after design verification, if you have any flaw, you can modify. And after fabrication in your wafer or in the die, if you have any issues, we have to throw off the die. That saves the packaging cost and final testing cost. So each place you have to test, and the defective products will be removed. If we have too much of defects after fabrication, that will reduce the yield. As much as you have large yield, your IC cost also get reduced. That is a basic idea in the VLSI design. So package test we have, and finally in the final version of IC, quality assurance testing we have. Even after performing all these tests also, nowadays in the market, our mobiles are getting busted. That we are seeing everywhere. What is the reason behind that? And then how much the level of testing they are doing. That also we have to identify. And basically with the basic laboratory based ICs, we can say like users also can test the ICs. For that only we are having additional pins in the IC. Through that we can test whether the IC is functioning or not. How we test the basic ICs, maybe AND gate, OR gate in the laboratory we can consider. We have an IC tester, that is separate part. If we enter the pin or like IC number, it will check whether that is correct or not. Even a single gate in the IC is defect, it will show that as a error only. But IC may have 4 or 6 different gates. When one is defect, your IC tester may show that as a defective one. If you test manually, remaining 3 gates you can use to perform your laboratory experiments. So like that, testing blocks we'll be having. These are the basic test models that we consider. One is design verification, wafer test, package test, and final testing for quality assurance. So basic things, designers are responsible for synthesizing the circuit to satisfy the design specifications and for verifying the design also. And design verification, this is used for ensure the required function when you go for a manufacturing. Required function in the initial level itself with the design specification we do have whether we are getting the same function or not, that we have to check. When the error is found, modification can be done before you go for a fabrication. But after fabrication, if you find error, the die should be removed, at least the packaging and other quality assurance testing you can eliminate. Even the next one, like packaging, if you find the final version, you don't have to leave that into the market through the quality assurance. After that also, if some faults are escaping through the ICs, that only coming into the market, which gives a random disorders like maybe accidents in the public places. So design verification must be repeated to ensure the accuracy. Some places we can say like multiple faults also. We cannot perform the testing with a single cycle. We may have to do multiple times to ensure the accuracy, particularly in the sequential cycle. We have to test repeatedly to identify some sequence numbers we must have. That we have to model. For that, we have to model our testing cycle. Repeated testing. That used to take more time, but accuracy compared to precision in the IC, these testings are not much important, we can say that. So that type of testing we have to consider, which is not major impact on the design means that we can go for. Otherwise, we have to test and remove to maintain the high precision. And can be considered, any design verification can be considered as a form of testing. So design verification, predictive analysis we can consider. This is to ensure synthesized design. The manufacturer will perform with the IO function, input-output function only. Quality of design we can check. Quality of our design we can check. That is what in the programming we are doing. And test, this is a manufacturing tester that ensures the physical device or the manufactured from the synthesized design has no manufacturing defects. This gives a quality of your device. This is what we differentiate between verification and testing. Verification we do for quality of design and test we do for quality of a complete device. So design specification in the behavioral architecture or register transfer level or logic level or physical level also we can do. And testing also we can do. Physical level in the transistor. Each transistor whether they are working properly or not. So for that also we have like so many techniques for testing physical or transistor level. But here the issue is when you consider very large application, testing from the transistor level used to cost more compared to a complete IC design and manufacturing. So most of the large applications we don't go for the physical level of testing. And logical level, gate level we have to test. There our faults must be projected in the output side, or maybe we have to project the output. According to that, we have to apply the input so that we can identify the fault, and we can have like some redundant models also inside to bypass if we have any error. And another one, register level, memory devices also we can use to access the input from the specific output from the specific block, and then we can test parallel to the regular function. And behavioral and architecture level also gives in the same form of testing. So behavioral level, we develop in high speed and integrated circuit simulated to determine the functionality. And register level transfer, logic function, data path and control circuits we used to have. And this must be verified for the functionality of our specific function. And logic level, verified to guarantee the correct functionality in the transistor level, specifies the physical level description of our device. Physical level description, normally in the transistor level, the final design and operating frequency specifications we can get through this. So digital verification, analog circuit, and mixed signal circuit. These are the, like nowadays in all the ICs, most of the ICs we are having combined these three. So what are the different techniques available for this verification? Digital verification, standard verification methodologies are available. We have to model the fault. Modeling fault says that you must be able to predict with any one combination. Not all the combination going to project the fault which is present in your logic circuit. Some specific like set of inputs only gives a function that we can say as sensitive inputs, sensitive to the fault. That we have to identify. We don't have to apply all the like test combination to the circuit. That is what we call as modeling of fault, and logic for fault models based on the logic functions, and fault detection through the fault model. You have to detect the fault, and then after detecting maybe a circuit you have some adder or something like that, some multiple blocks you are having, you have to identify the fault first, and then you have to locate the fault where you have exactly the fault, and you have to identify whether that fault is dominant or not. Dominant fault we used to say as maybe some blocks are available inside, some sub blocks are available. This may have some set of input combinations that identify maybe fault 1 and fault 2 and fault 3 all are available inside. But the small block is having only one block, like only one fault in this case. When you test the outer block or maybe the major block, it should identify this fault also. Then we can say that the fault test vectors which are generated for the small block or maybe in the sub block is dominated by the fault vectors that we generate for the larger block. That is, we call as fault dominance. And then through logic simulation, we have to identify. This is what we follow for digital verification. And analog verification using a circuit simulators, SPICE or master SPICE devices we can have. So analog functional verification we can do with the characteristic modeling only. The characteristics we have to identify, and according to that we can model that. We can use Verilog or Verilog AMS we can use mostly for analog, and mixed signal simulators we can use for testing purpose. And mixed signal verification, this is like a connectivity testing between digital and analog circuit using a very low analog behavioral model. Analog testing is, we cannot say like 100% good accuracy we can get. That varies normally with the environmental situation also. The characteristic varies with temperature also varies. That we have to identify with accurate. So verification using behavioral analog model also.
Sir, excuse me, sir.
Yes.
Sir, I have one doubt, sir.
Yes.
Sir, for digital verification, what are the things we have to follow, sir? Because all are zeros and ones, like the binary, we have to given as an input, sir. Logic simulation.
Yeah, we can say like some block or some circuit is open or maybe short circuited. Some small example
Yes,
we can maybe even small AND gate we can say stuck with some specific input.
Yes, sir.
This is stuck with logic 0. So as per AND gate function, we supposed to have output as 1 when you have input as 1. But here this is stuck with 0 continuously, you'll be having the output as 0. So if you apply any combination of 0, 0 or 0, 1 or 1, 0, you cannot say that you'll be having output as 0. You cannot say that the gate is so perfectly functioning.
Yes,
we have to so here the test vector which is sensitized to this fault, which is input is stuck at 0 in any one input. So in that case, the 1, 1 is the only set of input function or test vector that we can say that will project the output error into the output side. So here is a fault. So simply we can say as 1 over 0, 1 is the actual input, this is a faulty output. You're supposed to have output into logic high, but you will be having output as faulty output, which is 0. So through the functional comparison in the output side, you can identify. This is with a simple circuit. So here we can say that by applying input 1, 1, this fault is propagated to the output side. This is projected in the output terminal. So similar to that, each circuit or a functional block, you have to apply some set of input that should identify or maybe project the error which is present inside the digital circuit into the output side. So output side, the output response analyzer performs the testing procedure, that is by comparison. For comparison, you can do in multiple ways. Either you can generate the actual output. When you are generating, it should be so perfect. That means the testing circuit should not have any flaw. Or you can store the output responses in the memory, and through which what you are getting in this place can be compared with the stored existing or predefined accurate output value to which you can identify. This is I'm saying with a single gate. Even
Yes.
in large circuit also the same pattern we have to follow. So once the fault is detected, that is what I call fault modeling. So here fault modeling gives a test vector as 1. And logics also we have to identify, logics also changing or not, that we get through the output side. Here the fault is detected.
Yes, sir.
We have to locate the fault, whether it's available in the first terminal or in the second terminal. When you are applying different set of input itself, we can identify. That is one option. Or we can say as this is some predefined value or as a 0 value. By selecting anyhow, we are going to use all the 3 combinations only, like all the 4 different combinations. So in this combination itself, we can identify which terminal is going to have having a error. That is what we can say as fault location. Fault dominance normally with multiple circuit we can get, and this can be identified through the basic logic simulation. So here, if you perform logic simulation for this AND gate, for one combination will be having a different output, which is a error.
Yes, sir.
We are
So
going
what is the analog value you have to give in for this, sir? Analog testing.
value to characterize. That is the one difficult part in verification and testing procedure.
Yes, sir.
So there also in the CMOS level, if you consider in the digital form, whether through the transistor it is moving to one place to another place, that we can check. It is very basic transistor level. That also functional verification. Only the function through the transistor, whether logic 0 or logic 1 is transferring to the next node. That is one way. Another one, if maybe we can take an example of small ADC. Some analog inputs we apply, we supposed to get the digital output. Analog part alone we can consider. So small basic, maybe a small amplifier we can consider. So for that may have different characteristics. That analog circuit may have a different characteristics. So output node, some specific voltage we be supposed to have, or specific current we have to receive. For that, we have to characterize or maybe model the circuit to measure the specific voltage. Practically, we cannot have the accurate value. That is a major difficulty that we get through the analog circuit. That is a major difficulty that we get through the analog circuit. For that, your test circuit must be in high precision level. It should measure the values. Even moreover, we have a behavioral change with respect to environmental condition also. That normally we do through the SPICE simulation. We have to develop a circuit or we have to measure with a specific place.
So it may be LT space or a T space, sir?
All the SPICE tools we can do, because you are going to develop additional circuit only to measure or maybe to perform the model. So any SPICE tool that you use for analog verification, you can use. Or nowadays, most of these blocks that do in the mixed signal circuits, we can have a digital verification blocks for this analog mixed signal circuits, because output will be digital form. That we can verify through the characterization procedure. For that only I told the example of ADC. ADC we have different characteristics, static also dynamic characteristics. So any change happens in the circuit that directly reflect in the output side in the digital form. So the digital output can be verified through the digital models, and that identifies the error in the analog circuit. That means our mixed signal circuit. So for that, timing based analysis you can use, or functional based, or fault location SPICE based analysis also we can use. Is it clear, sir? Analog verification and mixed signal, analog and mixed signal circuits also, they did difficult, but we can verify through characterization. and manufacturing process to discard defective boards prior to assembly with expensive VLSI components. Here we can say like pair our board test for PCB fabrication and PCB assembly board level test we consider, and unit assembly, some units, multiple units you are connecting one to other, that we can call as unit test, and system assembly we can say a system level testing, right? So these tests also we performed for all the complete application that we are having. This is with the board and complete system level we can say. This is fast. Many specialized equipments also we do have for testing. So automatic test equipments we used to say ATPG are highly efficient analysis methods also available. Testing with the parameters as I told just before, like discussed for analog circuits in terms of voltage, current, or power factors, and harmonics and signal to noise ratio. These are the basic testing characteristics that we consider for analog, also mixed signal circuits. These are all the automatic test equipments that we have nowadays for testing purpose. So system level operation, this include single bit upset like electro migration, and material aging also gives effect of testing. And here one of the major test model that we use, boundary scan method, because this is very large in block. For this normally registers we used to include. I'll show you in the structure. So modeling, either circuit modeling or fault modeling we can do. Circuit that propagate the error in the output, and here only the logic values, either 0 or 1 variation that projected in the output side. And the simulation ATPG we can use, logic simulation, fault simulation, and test generation function also we can have here. And testable designs, two different parts available. One is design for testing, another one is built-in self-test. And finally, synthesis for testing, in which the first one is automatic test equipment or automated test equipment ATE, performs a test on a device, either device under test, equipment under test, or unit under test, which we are selecting, or using automation to quickly perform the measurements and evaluate the test results. Here there is a circuit modeling. This model abstract representation only. Here you can see in the circuit, the C1 and C2, C3, C4 are the actual circuit. These are the registers we are using. Through these registers, we can access the output response that we get through these circuits. And by accessing this, you can test either by applying serial inputs. You can see here, this is a circuit. This level you are going to test. The output of C4 can be stored in the specific register, and that can be verified by using a test vector. As we saw the general structure, input test stimuli we have to generate. Otherwise, we can apply the pre-generated data also. That is what serial input that we have. So this is testing input. So that we apply through this register, we can apply to the circuit for this specific input. What should be the output? That we know. So that we can test through the register, and we will get the test output also, whether as pass or fail. In between, we will be having control signals also. Most of the testing circuit used to perform little less speed compared to the actual speed of your circuit. The reason is the fault should not miss. So according to that, the testing also we call as basic testing procedure or at speed testing procedure, which follows the same speed of our actual circuit. And fault modeling, two different types we have. One is cause and effect analysis and effect and cause analysis. Cause and effect analysis enumerates all the possible faults and test responses to the given or maybe applied circuit, we can say. We know the cause, through that the effect should be analyzed. That means in the output response. And the effect we may have in the output response, through which the fault, through the backtracking you got to analyze. The process of actual response of UUT or unit under test as an effect tries to determine directly only the fault that could produce the response. Specific place, that means output you will be having, output you found as an error. So from which you have to identify the cause. Where is the actual fault? That is through locating. These are the two different approach we are using in fault modeling. Cause and effect analysis and effect and cause analysis. You can see here fault models. if we have 0 plus like some sigma value that we have through this, it is going to add maybe with some fault in this place. From this, you are going to have a different output, maybe as F1 and F2. So this is a actual like after with a specific stuck fault or maybe some specific fault, you are going to have this output. So in which you have to identify the actual defect. This is a response you are going to have, the effect that you have. So from this, any actual circuit available, you identify the exact location where we have a error that induce the sigma as 1 as additional value to each function. That is what modeling a set of the electrical failures that we have inside the circuit to be identified. Right? There may not be like a single fault. We will be having multiple faults also. So multiple functions we have to check and we have to set the model for identifying all the faults present in the circuit. ATPG with logic simulation. So logic simulation is a form of design verification testing only. Uses the model of the designed system, any specific system we used to consider. That is what basic level of simulation that we are doing. And as a treatment, known logic values are delay modeling or hazard detection, oscillation control, such due to oscillation any variations we have, and values needed for tri-state logics and mass circuits. These are the things that you can identify through this logic simulation. And fault simulation computes a response only from your circuit. So in the presence of fault, so you'll be having some set of output. From this, you have to compare with the expected output. If you have any variation, we can identify. If there is no variation, we can say that the circuit is fault-free circuit. So for this, initial stage is test generation. Process of determining the stimuli to test the digital system. To test our digital system. This is online testing method we can use. Do not require any test generation separately. All will be integrated together in the ICE. And here the popular one method that we use, pseudo-random sequence generator. This pseudo-random sequence generator we can develop for the specific faults present in your circuit. We don't have to develop a complete sequence. So automatic test generation can generate the test for the specific function. This is maybe a fault oriented or function oriented. Function oriented, if you consider all the combinations you have to develop, and for fault oriented, for the specific fault, what are the test vectors available, that alone you can apply. So the first one, fault oriented test generation. One tries to generate the test that will detect the specific fault, possibly locate the fault also. Function oriented, generate a test that if it passes through the system, you can identify, you can get the specific function. If you have any variation in the function, you can say that you have some error in the function. So for that, all the combination normally we used to apply. Stimuli and control circuit we have, and here as a simulation program, this is our internal model. From this model, what we are going to have as in the output side, and the result you will get in the result part through the output response analysis. So simulation based test benefits. Basic thing, we can check the error conditions and some conflicts, bus conflicts, anything available that we can identify. And the ability to change the like delay in case if you are having like worst case timing conditions identified in the circuit. And checking user specified values through the simulation process. And any desired state values are getting changed, that also you can identify. And precisely control of timing, particularly for asynchronous events, you can have. And provide automated testing environment also, that support also you can get through the simulation based test. And with RTL models that drives and observe the circuit during simulation that we can do. And here is our testable model. The first one is designed for testable. Primary inputs, as we discussed again, already, the same way we have a primary inputs through the test generation block we can apply. So here is the logic block. These are the internal buses. This is for logic block 2. In case there are some errors in this one, directly it will reflect in the output side. To test this, we don't have to like disturb the complete block. You have to identify actually where you have a error. So for that, internal buses you have to access. But one thing we have to remember, normally in the ICs, we cannot give all the internal buses or internal lines into like as a like pins for your IC. That is practically not possible. So in the specific places, you can place test input functions, and then you can test. This is a primary input in case if you want to test the block logic block here B, you can force the input in this place and you can test the output here. In case if you are getting perfect output, you can directly say that the error due to the block A. Like that, you can locate the error also exactly. So added hardware that reduces the test generation complexity and test application cost also. And this test generation complexity normally increases exponentially with the size of chip. That is also one thing. So what are the testable designs are available? Either you can introduce test points or initialization that we do normally through the reset function in the sequential circuit like flip-flop, and monostable multivibrator one-shot circuits, or oscillator or clocks we can use for controlling, a counter or shift register to access the in-between sections we can use, or partitioning large circuit into small circuit and each can be accessed separately, and logical redundancy that could be removed, or we can have when we need to bypass the specific error path here, or breaking global feedback path and scan register. These are all used normally in the design for Dept. These are the different ways also that we can have. And these test points normally we use for forcing some input. Maybe some sequence of blocks are available. So these are all connected here. Instead of checking the complete block, we can introduce some specific control at the test points here. Maybe here you can add additional gate which are some AND gate or OR gate. Here we have additional one pin that we can use as a control signal here. Initialization through the specific or additional control. Your initialization or normally in the sequential circuit, if you want to test, we must know the present condition. When it is running with a specific application, that is not possible. So you have to initialize with a specific timing, and then you have to go for testing. And monostable one-shot multivibrator. These we use as a switching function in between, through which you can add additional pins also or additional inputs also for testing purpose. And oscillator and clocks can be divided internally as local clocks or from the global clock, and each block can be tested. And counters and shift register we can add between the blocks. Maybe here is available like this. You can add in the last circuit also we saw here. And this can be applied as an input, and here we can have one serial input as a register function. And here the test results you can have. Like that we can add here, and logical redundancy that we can have in case maybe some tri-state functions, we have multiple functions are available. If any one function or path is not functioning or have a error, you can bypass it and you can get the output through the another circuit. But this is the additional block only that we use in this circuit. And breaking the global feedback path. Each path can be blocked or interconnection additional registers and counters you can use between, through which you can access the data from each subclass, and scan registers also that is placed between all the functional blocks. And another one method that we have, one of the latest method that we have, built-in self-test. This is having a capability of any circuit to test itself in the board or maybe in the system level itself. If you have IC, along with that you can have the test generator and output response analyzer also. You can apply the input through this test blocks or through the generation, or directly also you can apply. You can have a separate control signal. Through the control signal, you can select the mode as a normal function or maybe the testing function. I'll show you the structure. So built-in test equipment refers to the hardware or software incorporated into the unit to produce DFT BIST capability. So here defined in two different forms. One is online BIST, another one is offline BIST. Online BIST includes concurrent and non-concurrent testing techniques also. Offline test which include functional and structural approaches. These two are the different approaches that we have with the offline based. And online based, we can have with the concurrent and non-concurrent test techniques by selecting or enabling into the test modes. These are the types we have in the best form of testing: offline testing and online testing, functional and structural, and concurrent and non-concurrent. Offline deals with the testing of a system which is not carrying out any normal function. This is normally in the system board and chip can be tested in this mode. This offline mode. Online testing occurs during the normal functional operation itself. So for concurrent testing, as a first one, testing occurs simultaneously with the regular function, usually accomplished with the coding techniques or maybe duplication or comparison procedure that we can have for testing purpose as output response and data. And non-concurrent testing carried out while the system in ideal stage only. So often accomplished by executing the diagnostic software or routines are macro codes. A diagnostic firmware routines as micro codes we can have for testing purpose, not parallel with the regular or concurrent functions. This is a testing model that we have for large SOCs. We can have here. You see here, this is what we say is built-in self-test. This is a BIST circuit. This used to have a controller, test generator, and output response analyzer. This is a core that we have to test. So these are the buses available. Either you can get directly input from this one, or you can generate through the BIST also, and you can get the response, and the BIST response you can apply to the test controller, which identifies whether the core is working properly. So like that, each core you can have. SOCs are like very large system only, which are having too many number of cores to get the complete system in your chip. It may be a digital block or memory block or like analog block or mixed signal type also. So this reduces the testing time, and memory cost also reduces. Normally generation we used to consider for fault oriented only. So for the specific faults we can those model only we can develop in the BIST setting. And power consumption also very less normally in the inside the ICs, and hardware cost also reduces. Test quality also high, which says that we can access all the internal nodes since it is available inside the IC itself. These are the motivation for the BIST. Need for cost effective testing, and doubts about any structured fault model that we can get through this, and increasing difficulties also normally in the ICs that we can perform through this BIST model by having inbuilt test generation, and growing the volume of test pattern data that also we can develop, and cost effective also, and test application time, and it reduces the gap between the tester and unit and the test speeds. Drawbacks: additional pin you have to give, and additional silicon area we use for BIST circuit in addition to the actual or circuit which is considered on the test. And device reliability due to increased silicon area that also decreases here, and performance impact due to additional circuit also we have to take it, and additional design time for BIST and additional cost also we have to spend on that. But compared to precision, this is not like a very major issue in online testing. So basic is circuit under test, test pattern generation, output response analyzer, and distribution of a system for data transmission between TPG, circuit under test and ORA, and BIST controller. These are the major things that we have in the built-in self-test. And the last one, synthesis for testability. This refers to one specific area in which testability considerations are also incorporated during the synthesis process also. Here two different major sub areas we have: synthesis for full testability and synthesis for ECE testability here. So full testability for a complete circuit we supposed to develop, and ECE testability only for the specific fault we can model inside the circuit. That is a basic difference. And advantage is like less test generation time, and less to test application development time also, and high fault coverage we used to have. And synthesis for ECE testability also has potential for realizing a circuit with less hardware and delay overhead than DFT. These are the different tools available normally for testing purpose. I'm not familiar with all the tools. So Atlanta, this is automatic test pattern generator for combination circuit. Maybe I will share this fault simulator for combination. Many are available for digital circuits only, and very few that we can do through particularly for mixed signal circuits we can have particular design models only. Maximum it supports for test generation and output response analyzer using memory or without memory by comparing or directly performing the characteristic verifications. And rule checking, test planning, and integration verification. These are the different things. Popularly in institutions, we are using Synapsys and Cadence. Synapsys DFT compilers are available for ScanChain, and Synapsys Terra Max ATPG generators also available. And memory-based technique also we have in Synapsys. Synapsys design compiler, DFT compilers we have. Cadence also conformal, conformal that we have. Xenium, these are all like a basic tools that we have for testing purpose. We can model, we can have for this complete testing. If you have any doubt, maybe you can ask. We can we cannot practice all together. Maybe based on your application or maybe based on the requirements, we can select the specific tool also and specific technique also according to the only we have.
Sir?
Yeah.
Audible, sir? Are you...
Yeah, yes, sir. You are audible, sir.
Sir? Sir? Regarding the development of ASIC design and mass transistor design, sir.
Yes, sir.
The first sessions are told that there is a special type of FinFET, like that there is a special type of ICs to be in practice in USA, California University, like that, sir.
Okay, sir.
Apart from that, any type of research will be going on in ASIC design, sir, nowadays? ASIC design chip.
Yeah, ASIC design is going on, sir. That is particularly like many, even India also many different applications we have. There is a design center,
Yes, sir.
In Andhra Pradesh we have, and in IIC Bangalore
Yes,
also ICs they are developing. That is,
yes, sir.
they have an industry mainly concentrating on Germany based also. That is particularly for high precision defense application only, not for commercial purposes. And nowadays many
Yes, sir.
devices and the new kind of applications also we are getting. Initially, if you say like simple computer basic processors only we are having, in which some are standardized, not everything. Like
Yes,
shown as a first example, small toys, if you are having everyday new toys are arriving to the market. We cannot use the same or maybe the previous one to the next one. If we have additional function that should be customized completely. So
yes, sir.
for that, they must check the market value. So if you go completely for new design, there we have to check the market value. Since they are going to spend too much of time also cost on the new design, and to get they must get the profit also back for commercial version if we consider.
Yes, sir.
So everywhere they have a design, new design models. Not only we are stopping with a specific model. If you see like very old structures, basic digital structures only be available in the ICs. Analog ICs we do have separately, not like nowadays. Nowadays we are saying simply as SOC, which is having even antenna basic supporting models also inside. And
Yes,
analog
sir.
circuit, mixed signal circuit, everything available in the single IC core, or we can say a single die.
Yes, sir.
Yeah, like that we are developing each and every day new device and new design is coming up. And
Yes,
there
sir.
also like fully customized or maybe semi-custom. That is only differs there. So commercial functions, as I gave as an example, you simply observe the market nowadays. Samsung or maybe Apple, they are saying that with this time duration, we are going to launch the new device. And
Yes,
with
sir.
additional features also, for those additional features, they will go for the full custom design. They will design these are the additional features or additional applications they are going to add. But after giving the time duration, they have to complete all the process within the time. As I had a discussion with one of my friend who is from Samsung. He is from testing side only. So they use the standardized test blocks only to build the complete design. So after getting complete design, they do the basic verification and shift completely into the testing part. They have to complete the testing procedures. So with the
Yes, sir.
application they need for the specific mobile phone, not with the all other possibilities. What happens in case if you are having like any other function or maybe overload function if you have that they won't check like basic model within the duration, whatever the
Yes, sir.
possible, whatever frame that they will check and pass into the market. And we can see nowadays in the market many versions are coming up after seeing or after checking some like disasters outside in the market, they are refining the device again. So that also happens as a sequence wise. Some cells are available as standardized one, that also not for a long time because technology also one side is getting minimized. So
Yes,
for the
sir.
specific period, they will have this standard cell-based design also, like as a semi-custom. And so many companies also available nowadays in the market who are ready to produce multiple standard cores to the manufacturer.
Yes,
If
sir.
we see mobile phone, that is not from the single vendor. Each and every device from comes from different like manufacturers. And each IC has different cores which are coming from other some people. But here the final version only says the brand.
Yes, sir.
Like that,
Thank you,
with
sir.
the application we are getting every day. We are revolutionary improving every day.
Yes, sir. Yes. Very much. Thank you for it, sir. Thank you, sir.
Thank you. Thank you.
Thank you, sir. On the behalf of Department of ECE, MSAJCE, I take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this FTP on VLSI and chip design organized by our institution. I thank our resource person, Dr. M. Sendil Sivakumar, sir, for this informative session. Clearly explained the concept, sir. I hope this will be very useful for our participants and faculties. We are really enlightened with your knowledge and presence, sir. We are thankful to our management for their motivation. I would like to thank our principal sir and HOD ma'am for their enthusiastic support. A special thanks to our organizing committee, teaching and non-teaching staff for their unflinching support and coordination. Last but not least, our heartfelt thanks to our participants. So with this warm words, we move to the end of this session. And thank you, that dear participants. The next session will start sharply at 2 p.m. for valedictory. The assessment and overall feedback link will be shared in the next session. Thank you, sir. Thank you so much, sir.
Thank you, ma'am. Thank you all.
Thank you, sir.
Thank you, sir.